Hi there. Today we're going to learn about orthogonal trajectories. By definition, orthogonal trajectories are a family of curves in the plane that intersect a given family of curves at right angles. Now this means that if there are two curves, that is, one is a circle, we assume that this is somewhat a circle, and we have another circle then. And when we draw tangents to those circles, we will have a set of tangents which are perpendicular to each other. So those set of tangents will be known as orthogonal trajectories. Now let's look at another example. Here we have two circles. If we have another curve, for example, we have a parabola like this. So it's passing and almost a parabola, and we have a tangent to this parabola like this, and another tangent to the circle. Now both these tangents will be perpendicular to each other if the set of tangents which are perpendicular to each other at that point, those set of tangents will be known as orthogonal trajectories. Now let's look at how to solve these type of problems which include orthogonal trajectories. Let's have a look. Now if we have an equation in the form of mx plus b form, y equals mx plus b, in this form, when we differentiate it, we get a slope of this form. The slope of the equation will be dy by dx equals m. This is the slope of this equation, equation 1. Now if you look at m over here, m is also a function of y and x, and it changes with the changes in b. So from this equation we get m equals y minus b divided by x. When we put this in equation 2, we get dy by dx equals y minus b divided by x. Now this is the slope of this equation, and we know from basic trigonometry, or actually basic differentiation, when there are two tangents and they're perpendicular to each other, we have the formula that links them, the m1 m2 equals minus 1 formula. But from this formula we denote this as m1. Let's say this is m1. Let's say the slope of this equation is m1. Let's call it m1. So we have the equation, the slope of the orthogonal slope. Let's call it the orthogonal slope, OT equals m2, which will be equal to dy by dx minus times of x divided by y minus b. This will be the slope of the second equation, the orthogonal slope. This equation over here, not that every equation is like that, but this equation, this particular equation over here, can be variably separable. It does not mean that every equation has to be variably separable. So let's look at this. We can variably separate this. We have dy by dy times y minus b equals to x dx. So when we integrate this equation with respect to y and with respect to x, we get y squared over 2 minus b y times b equals, this is minus, yes, minus times of x squared divided by 2 plus some constant. So we see that in this particular example, we have an equation which relates to, this is parabolic equation, I guess. So we have a parabola tangent to it, like this, maybe. Let's look at an example. Let's look at a numerical example. I have my question over here. Let's write this question down. We have an equation x equals to ky squared. X equals to ky squared. And you can see this equation is the equation of an ellipse. Rather, yeah, this is the equation of an ellipse. So when we differentiate this equation, we get 1 equals to k times 2y dy by dx. This is the slope of this equation. Now k can be related to this equation in the form k equals y squared divided by x. You put this in this equation over here, and we'll get what? Let's put it in this equation, dy by dx. 1 equals y squared over x times 2y dy by dx. So you'll eventually get x over, something wrong with this. Oh, sorry. So it'll be x over y squared. X over y squared. This y cancels with this y. We get dy by dx equal to y over 2x. So this is the slope of this equation. And when we want the orthogonal slope, we just add them. We just multiply it by minus. We just turn it over. Let's turn it over and multiply it by the minus sign. So we get the orthogonal slope equal to dy by dx equals minus 2x over y. So this is the orthogonal slope. Now this equation is also variably separable. We can variably separate this equation, and we'd get y times dy equals minus 2x dx. You'd get this. Now, when we integrate this equation, we get 1 over 2y squared equals minus 2 over 2x squared plus some constant. Okay, this, I forgot to tell you this. This is some arbitrary constant. This is some arbitrary constant. So don't worry about it. It gets cancelled in the process, and we get another equation. So we get this equation eventually, and we can cancel this and take this on the other side. We get 1 over 2y squared plus x squared equals to c. So this is the orthogonal. This is the equation of this curve, which is making a tangent with this curve. This curve is making a tangent with this curve. So you get the idea. Thank you very much.